Good morning, Physics 12. This week is our last week of just electromagnetism as itself before we move into a slightly new topic of electromagnetic induction. We're going to finish off. Last week we talked about what happens to a charged particle as it moves through a magnetic field. And we saw that it was very similar to current. In fact, we could use right-hand rule again. Remember, we'd use a right-hand rule if we were talking about movement of positive charges, or if we were talking about conventional current. And remember, conventional current is the idea that charge flows from the positive to the negative end of a battery. So that's what we use our right-hand rule for. And just to recap, so index finger is direction of motion of positive charges. So whether we were talking about positive charges in a wire, in which case we're talking about conventional current, or if we were talking about positive charges as in a positive ion or a proton that was moving along, the index finger still points in the same direction in both cases. Then we had our three fingers. These were our magnetic field. And then we had our thumb, which was our direction of force. So that could be a force on a wire, or it could be a force on a single proton moving in that direction. And then when we had our left hand, that would be used for negative charges. So for example, a negatively charged ion or an electron, or it could be for electron flow. So electron flow is maybe a more accurate way of looking at a circuit, because we know that it's not protons that are moving from the positive end of a battery, following along those wires, then going back to the negative terminal of a battery. We know that it's actually electrons that are flowing out of a negative terminal. The electrons are free to move, and so they move towards the positive terminal. So it may be technically more accurate, but we just go with the conventional current idea anyway. So this is kind of a recap of the last 2 weeks and our right hand or left hand rule. So left hand, same idea, index finger is the direction of motion of the electron or the electrons in a circuit. The three fingers are still the field and the thumb is still the force. So what we know, if we think back to a unit we did a couple of units ago, when we were talking about circular motion, well, we know that anything that's experiencing a force that's perpendicular to its motion, or so in this case here, a particle is entering magnetic field, and if it's perpendicular to the field, it's going to experience a perpendicular force again. Now it's perpendicular in the third dimension. So, if a charge, let's say we have a proton moving in the x direction, and all of a sudden we have a magnetic field that's in the y direction, and we know that our force is going to be in the z direction, so it's going to be like out of or into the page. But nonetheless, this particle is still going to experience a perpendicular force. It's traveling in the x and it's experiencing a force in the z, or it's traveling in the x and the field's in the z and it'll experience a force in the y. But either way, when something is experiencing a constant force that's always perpendicular to it, it's going to travel in a circle. So let's look at an electron moving through a magnetic field. So in this case here, we're going to use our left-hand rule, and let's assume for the moment that this electron is moving in a circular path. So what direction would it have to be in order for it to, as in, is it going to end up going clockwise or counterclockwise if the magnetic field is into the page? So what I want you to think about here is we need to align our magnetic field with the direction of these x's. So remember, an x indicates into page, and a dot, usually a dot in a circle, is out of page, like the arrow analogy I gave you. So if an arrow is flying away from you, you see the feathers on the back, that means it's going into the page, it's going away from you. And then if you see the point of the arrow, that means it's coming towards you. So let's line up our hands. So we're going to line up our three fingers so that they are aligned with the magnetic field in this case, which is into the page. And what direction is the force going to have to be if it's following a circle? Well, let's think back to centripetal forces or centripetal motion. And we remember that centripetal means center seeking, so we know that the force is going to have to be into the circle at all points. So again, this is a bit of review from previous topics, but we know that the force, when something is moving in a circle, the force is always in towards the center of the circle. So what direction is the electron going to be moving then? You can pause the video and you can try it for the proton as well. So pause the video and we'll try both of these questions here. What direction is the electron going to be moving on the left-hand side, as in clockwise or counterclockwise? And what direction is the proton going to be moving, as in clockwise or counterclockwise? So pause the video here and try using your left or right-hand rules to answer these questions. Okay, so if you are back, I'm assuming you've tried these problems yourself. So let's line up our fingers. We've got our 3 fingers pointing into the page. And so that's going to be into the page here for my 3 fingers. My thumb at the top, at this point up here, is going to be downwards because it's pointing towards the center of the circle. And because I'm using my left hand, that tells me that the direction of motion in this case must be to the right. And so it's going to be, I'm not going to finish the whole circle here for obvious reasons, maybe, but you can see here that it's going to travel in a circle. It's going to be following a circular path, and it's going to be going clockwise in this case here. Now for the proton, I'm going to use my right hand rule. So in this case here, my 3 fingers of my right hand are still going to be into the page. My thumb is still going to be downwards in this case at this top point here. And so when my thumb is downwards and my 3 fingers are into the page, and that means my index finger indicating the direction of motion is going to be to the left, which means that this is going to follow a circular path. It's going to be counterclockwise. Okay, so just to, again, to recap from circular motion, a couple of important things. So for one, circular motion means that forces are perpendicular to motion. So that's one fact that we know about circular motion. The forces are always perpendicular. And we also know that there is no gain in energy. So when something is traveling in a circle, there's no gain in energy. And the reason for this is we know that the formula for work done is force times distance times cos theta. Well, the theta between the direction of motion and the direction of force is always 90 degrees, and cos of 90 is equal to 0. So the work done is always going to be 0, and therefore constant energy. Okay, so just a couple of reminders, important things about circular motion. So let's give some real-world examples along with some questions. So a nice real-world example is actually a homegrown example here at UBC. So particle accelerators typically have, from the smallest to the largest, there are a few linear particle accelerators, but they're kind of limited to how far or how fast they can get particles going. And the reason being is that it's going to come to a dead end eventually, so you only have a limited amount of time to get those particles going faster. So most particle accelerator designs, most modern ones, except for there's the Stanford Linear Accelerator. That's the most modern linear one, but besides that, almost all major modern accelerators are circular. So think of like CERN in Geneva, Switzerland, or UBC Triumph. So this is a circular particle accelerator. They use magnetic fields to bend beams of charged particles. So what they do, and I'm actually going to zoom in a little bit here just to give you an idea of what's happening here. What they actually have is between these two plates. So they call these two parts here. These are called Ds because they're shaped like Ds. That should be an obvious one there. And in this area here, there's a magnetic field. So in this case here, they are firing positive hydrogen anions, which is essentially a fancy word for a proton. So they're firing these protons, and they travel in a circular path. So first of all, you can pause for a second, or just think about this for a second. What direction is the magnetic field facing in these Ds? So if the particle is moving this way here, following this path, it starts in the center and goes outwards, and it's obviously going counterclockwise. So if we pick a point, let's pick a point right here. Actually, it's probably easier over here because my hand's more flexible to go in this direction. So it's going in this direction here, and the force is obviously in this direction here. And so the magnetic field must be into the page. So if you've got your index finger pointing upwards, your thumb pointing to the left, and your three fingers are going to be into the page. So magnetic field here is into the page. Okay. And what also happens here, the reason why there's a gap in between here, between these two Ds, is because in this little gap here, what they do is they rotate the direction of the electric field. So at one point, so remember if it's going across the gap this way, for this point here, then that means it's going to, if you want the electron to go faster, or sorry, it's a positive particle. You want the positive particle to go faster, then you're going to make this plate positively charged, and this side of the metal D is going to be negatively charged, and that way the proton will gain some speed. It'll be repelled by the positive plate and attracted to the negative plate, or you can say that the field is going to be to the left, and so it's going to accelerate to the left at the positive charge. And then when it comes back around here, they time it so that when it comes back around here, they switch it. So now this is going to be positive plate. This will be negative, and it goes a little bit faster. So every time it goes across the gap here, it gains a little bit of speed. Because it gains a little bit of speed, it's going to end up having a wider path. And we'll see why in just a moment. So the radius is going to be dependent on the speed, so it gets faster and faster and faster. As it gets faster, it needs a wider radius to turn, and until eventually it reaches the outer edge and it's fired in this direction outwards here. So UBC, this type of device here is called a cyclotron. Let me just, I think it's called a cyclotron. Yeah, this is called a cyclotron. Yeah, there you go, cyclotron. So this is the largest cyclotron in the world. There's different types of particle accelerators, like the one at CERN is very different from this, but this is the largest of its particular kind. So they can get speeds of up to 75% the speed of light. Remember, the speed of light is times 10 to the 8 meters per second, and they use a 0.42 Tesla magnetic field. And we know that the mass, so we saw with relativity that the faster something goes, the more mass it gains. So the mass of this at this speed is no longer 1.67 times 10 to the minus 27, it's around 2.524 times 10 to the minus 27. So then the question is, what is going to be the radius? So we know that at this outer edge here, we know the speed, we know the magnetic field that it was going to, and we know the mass, and so we're going to try and find out what is the radius r. So this would be a tricky question to answer. However, I'm going to give you a little bit of a hint. The hint is we do have to go back to circular motion because this whole week is about circular motion. So just a reminder, circular motion, the formula for centripetal force is mv squared over r. Now, if I was going to look at a free body diagram for the particle at this point here, we can ignore gravity for a proton. It's just so small, it's really negligent compared to the force that's being applied to make it follow the circular path. So there really only is one force, and that is the magnetic force. And remember for this, that was going to be Q times V times B, where V is the velocity here. So this is the clue I'm going to give you, is that the centripetal force is the magnetic force, Fc equals Fb, and therefore mv squared over r is equal to qvb. So you can pause the video here and try solving that question for yourself. All right, so if you're back, I'm assuming you have tried this out for yourself. So let's solve this problem here. What we have here is mv squared over r equals qvb. You'll notice we can cancel out one of the v's. We're trying to find the radius in this case here. So if we rearrange for radius, we're going to have, let's just put this up here, r equals mv divided by qb. So what of these do we know? Do we know m? Yeah, we do. Do we know v? Yes, we do. We do know Q. It's not given in the question, but remember the charge of a single particle. So this is charge of an electron is going to equal the charge of a proton, except the electron is negative, proton is positive, and this is going to be 1.6 times 10 to the negative 19 coulombs. So it's just an extra fact that you have to have in your back pocket there. And so let's solve this here. This is going to equal 2.524 times 10 to the minus 27 multiplied by 0.75 times 3 times 10 to the 8, and we're going to divide that by 1.6 times 10 to the negative 19 multiplied by 0.42. So let's put this in our calculator and see what we get. So 2.524 times 10 minus 27 times 0.75 times 3 times 10 to the 8, and we're going to take this and divide it by, I'll put it in brackets, 1.6 times 10 to the negative 19 multiplied by 0.42. And that gives me 8.45. So that is the correct answer. The outer radius R equals, what's happening there? Okay, so R equals 8.45 meters. And do I have the correct number of sig figs? Let's see. No, it should be 8.5 meters. Okay, so there we go. The particle accelerator at UBC accelerates particles to 75% the speed of light because they have an 8.5 meter radius cyclotron. Okay. So another similar application to this is called a mass spectrometer. So the cyclotrons, these are used to understand particle physics. So essentially these, or things like CERN, for example, what they want to do is understand what's happening at the core of matter. So they want to go dive deeper into, beyond the scale of protons and neutrons. And so they'll smash hadrons together. A hadron is something like a proton or a neutron. So they smash these protons together at huge speeds, and they can create a bunch of extra particles. So they break down, and we can see evidence of quarks. So, for example, 3 quarks make up a proton, or 3 quarks make up a neutron. There's a whole particle family that could easily be a whole unit in and of itself that we're not going to go into, but they want to dive deep into what is the nature of matter, what is it that makes up protons and neutrons. And so that's what this whole particle physics, particle accelerators are for. Nowadays, the one at UBC is largely used to create medical isotopes. So they smash these hydrogen ions in other particles to make various medical isotopes they use for like radiography and things like that. So that's one of its main purposes. So another object that uses this idea of charged particles moving in a magnetic field is a mass spectrometer. So a mass spectrometer, what the point of a mass spectrometer is to find a sample. So you take a sample and you put it in here in this gas chamber. So let's say you want to know what a certain gas is made of or what a certain material is made of, and so you ionize it either by heating it, or you basically fire electrons at it, and that's going to ionize it, and you have to either heat it up as a gas, or some things, like if it's a liquid, you put it under extreme low pressure, so you make this into a vacuum up here, and that can vaporize it as well. So nonetheless, you have this gas, and you want to know what's in that gas, and so how you do that is you fire these positive particles in this direction here. Let me just sorry, in this case here, they're going to be negative ions based on the picture here. Yeah, negative ions going that way. Yeah. So in this case here, we're assuming it's negative ions. Usually these are positive ions, but the picture's backwards, so don't worry about that. So you take these ions, you accelerate them in this direction here, and they're going to go through, this part here is called a velocity selector, and we're going to see what that means down here. So this is the velocity selector here. And then it goes into the vacuum chamber, or it goes into this area here where it essentially separates the beam. So you have this velocity selector here, which essentially forces you to have only a specific velocity of particle that travels through here. Now, as these particles come out here, they're in this magnetic field area, and they're going to follow this circular path. So they're going to follow 1 or 2 circular paths. Now, this is something I want to highlight, because your weekly homework question is related to this. So please remember this. This distance that it travels is twice the radius. So this is the radius from here to here. If it's following a semicircular path, it's going to go from here along to this point over here. So it's actually, this distance here is going to be 2 radii. So this is 2r right here. That's the distance path from where it enters until where it hits against this detector over here, the radial It's 2r is the distance there. So just to figure out the radius. So in this first question here, it's not a mathematical question or it's not a calculation question, it's just more of a formula question. So if you want to find the charge to mass ratio of an object, you can do that using this here. So in order to solve this, the first thing you need to do is the same thing as the first thing we did up here. We're going to set that centripetal force to the magnetic force. So what I'd like you to do is do that. Set the magnetic force to equal to the centripetal force and try and find an equation that gives you this ratio, this charge to mass ratio. So pause the video here and try and find that formula. Okay, so hopefully you're back after trying that. So let's give this a shot. So we know FC equals FB. And that means that MV squared over R is going to equal QVB. Like as before, we can cancel out those V's. And we're trying to find a charge to mass ratio. So I'm going to divide this side by M and this side by M. Those cancel out. I'm going to divide both sides by B. And so I'm going to have this charge per mass is equal to V divided by RB. And you can see that we could also isolate this for R. So R is going to equal Vm over QE. And that will come in handy for the weekly assignment as well. So this is our charge to mass ratio. Now with these accelerators here, with these mass spectrometers here, if you have something that has twice as much charge, it's going to have a very different path. So it's not going to jive very well with either of these. And plus, yeah, so essentially you would see that it wouldn't really match up with the rest of them. So if we assume that all of these have the same charge, let's assume that they're all +1 ions, and we can identify which ones are +2 because they'll be wildly different from everything else here. So if we can assume that we can identify the charge of each of these particles that's moving along this path, traveling along and hitting the screen over here, if we can assume that they're all the same charge, then we can identify exactly what the mass is going to be. So based on the radius, and we know the velocity because we've used a velocity selector, this thing here, which we'll see in a minute, only allows particles of a certain speed to go through. So we know the velocity, we know the charge, we're assuming they're all +1 because the ones that are +2 we would be able to identify, and we know the magnetic field because we set that ourselves. So we can find the mass of each and every one of these particles. And so what this mass spectrometer does is you can take this sample of gas, maybe it's a type of medicine that you want to identify what is in there, or maybe you're trying to do some botany and trying to find what chemicals make up a certain enzyme in a tree sap, or whatever it is that you're trying to do. You put that substance in here, it's ionized, and so these ions from this substance are going to travel through here. They'll all have the same speed as they go through here. And so you can tell, okay, this one has a mass of 250 atomic mass units. So this one must be uranium. This one here has a mass of 12. So this must be carbon, for example. So you can identify what the different substances are. And you can also even identify different isotopes. So let's say you have a sample and you wanted to know how much of it is carbon-12 and how much of it is carbon-14. Well, these would end up having very slightly different paths. So you could tell this one has an atomic mass of 12, this one has an atomic mass of 14. So you can identify what those different parts are, so the different elements that make up this sample. Okay, so last thing is about a mass spectrometer. Like I said before, we want to make sure that all of the particles that are traveling in this chamber have the same speed. If they have a different speed, then we wouldn't be able to tell, okay, is the speed twice as much and the mass half as much, or is the speed half as much and the mass is twice as much? So you need to make sure that the V is a constant. And you do this with something similar to what we saw last week with the J.J. Thomson experiment. If we have particles that are moving, we're going to have a magnetic field and an electric field. Now, for a positive particle, the electric force, Fe, is going to be downwards. And if we use our right-hand rule for this, we're going to see the particle index fingers pointing to the right. My 3 fingers would point into the field or in this general direction here. And so the force is going to be upwards. So we're going to have Fb being upwards. Now, Fb depends on the velocity. So the force B depends on velocity, but Fe doesn't. And so if we look at this before, again, we saw this with last week's assignment. We had these two forces, so QVE equals Q times the electrostatic, electric field. So again, our Q's cancel, and our V is just going to be the electric field divided by the magnetic field. So if we set these to a certain value, if I set this and this to a certain value, I know exactly what the V is going to be. Because what's going to happen is if this particle is going faster than this V, then it's going to have a greater FB. And if it has a greater FB, it's not going to be able to travel straight through that hole, so it's going to hit this plate up here, and it's going to miss. If it's traveling too slow, then the magnetic force would be less than the electrostatic force, and so it's going to have a smaller upward force, larger downward force, and so it's going to start accelerating downwards, and it's going to hit the plate somewhere down here. It won't go through the hole. So this ensures that we can, by setting up the magnetic field and the electric field, we can choose exactly what speed we want for our ions. Now you'll notice it doesn't matter for the Q. If it's a 2Q ion, then this is going to be 2Q, and this is 2Q. It'll still cancel out either way. So this doesn't select for charge, it only selects for velocity. But again, just by looking at other data samples, you would be able to identify which one doesn't really make sense for these particles here. So in the part here where you're differentiating what the different types of atoms or ions are, you'd still be able to disregard the ones with 2Q or 3Q because they just wouldn't match up with the rest of the particles. They'd be quite an anomaly. Okay, so that is it for the learning of this week. You've got one more assignment that's online, and I'm hoping you'll do at least 5 questions out of the 13 or so. So give these a try, and yeah, if you have any questions, come by the weekly Fit Block on Wednesday. Thanks very much.